Okay, so welcome to today's lecture in neural networks and deep learning. Today we'll talk about large language models. We have covered them already a bit on some fields, but today I'll try to make a bit of a summary of how these language models work, what their challenges are, and that also gives us already a bit of an opportunity to look back at some things and yeah, see it as a bit of a repetition. Therefore, I also have one additional announcement before. Maybe you've seen it. I think it's on the website already. We had to do a bit of a shift at the end of the lecture. So normally in the last week, I do a repetition lecture. Since I'm not available in the last week, this lecture will already be on next Thursday. So we'll have next Thursday already the repetition. Then on the last week, we also have an exercise in the lecture. And of course, this lecture is also part of what we covered and can be covered in the exam. We'll just do then a summary of everything except this one topic. I hope that is possible. And for the repetition, I mean, I can of course do just an overview of what we have done. But if you have specific questions, specific topics where you said, oh, we should cover that in more detail, then please send me email or contact me somehow. Then, of course, I have a bit more focus on that. So it's your chance to guide a bit how the repetition will be and take the opportunity. I can imagine that most of you haven't started yet preparing for the exam, and that's completely normal. But yeah, if you already see there are some things which should be addressed in more detail, then please contact me and then I can try to cover it. But let's start with large language models. So what we want to do about that is we'll do a bit of an introduction, then we'll look into the architecture. And in the architecture, we mainly not look, I mean, the architecture you hopefully will see, you'll know that all the things, how a language model is built. What we are a bit looking into what people call scaling laws. So if you want to build large models, there's several hyperparameters which influence each others. So normally you have a bit of a limited compute budget. So you can spend 5 million on building a large language model, but not more. And then you have to decide, oh, should I use more data or train a bigger model and so on. And there's some ideas of how we can hopefully get a good estimation. Then we'll look into inference. And there's one thing which is, of course, very interesting in large language model is this type of prompting that it can use, solve many tasks, that it can do what is called in-context learning, so complete some examples. And so you can have a quite different type of learning than what we normally do. We don't have to update the model, we don't have to change the model, but we can give it as examples. And finally, we look into training. We'll look a bit in instruction fine-tuning and a bit in reinforcement learning there. There's no reinforcement learning, so it's only like a brief overview on how this is used in large language models. Good. So let's start with what a large language model is. I assume you're using on frequent basis large language models. You can ask something like, was ist verarbeitet natürliche Sprache? And it gives you an answer, it generates the answer, and often, at least when you first use them, there's surprisingly good answers in that. And that's what we want to investigate today. How can the models be so good in some time of interpreting this type of language, dealing with the ambiguities and answering them, which was very, very difficult for a long time. Especially you can describe the task somehow now in natural language and not like as we are doing it normally in neural networks. You train it for a specific task to predict. So you can distinguish cats and dogs, and then you can only distinguish cats and dogs. You can give a natural language description of what you want to do, and then hopefully the model will perform the task. The nice thing a bit of this is that the general architecture, the general model is really straightforward. There is nothing super new about it. We talked a bit about language models, and so they have been around, language models, for 30 years, like 10 years already. There's neural network-based solutions. So what it really is typically that you just predict the next word. And we've seen in the self-supervised lecture that this is a very nice way of training, and it enables us to do to encode so much text. What the large is two things. So it's on the one hand, they're typically having many parameters. So we'll see that going up to like 100 layers and so on. And of course, also the data size. So there's huge amounts of text where this model is trained on. And in general, these large language models are typically like one example of so-called foundation models that are any model that is trained on broad data. Typically in self-supervised learning, it doesn't have to be typically that it directly can solve, or with the idea that later you fine-tune it to solve a lot of tasks. So that's like this transfer learning approach is in there. You build the base model and then you can apply it. There's other terms like large language model that is typically only for text. That's we cover today, but I guess you've heard about that there's more and more multimodal models that can not only understand text, but also audio, text, images, and so on. There's called sometimes pre-trained model and self-supervised learning. Good. Any questions to the general idea? Okay. Then we can start with what is the architecture. And the architecture is something that we mainly know already. It's like that we have decoder-based models, so conditional models. And if you remember, we have all these models like encoder, decoder, and encoder-based models. And when we're talking about large language models, the basic assumption is that we have a decoder-based model. We'll come to that. I mean, we have this decoder only and encoder decoder based models. One big advantage of these ones is that it's somehow easier to pre-train them. So do self-supervised training or more efficient to do that than an encoder decoder model. Because we can directly always predict the next word. We get a lot of feedback signals with one single sentence, and that is a significant advantage of that. Comes decoder-based models we saw come with a bottle or like with a disadvantage. It normally means we are doing left to right processing, so we don't have bidirectional information. However, since we process everything at the end, we still have all the information. With transformer-based architectures, information flow is quite fast, so that is possible. But it's important to keep that in mind, which might be a bit surprising that we can get this strong performance with purely decoder-based models. And then, of course, it doesn't need to be a transformer, but we're honest, the default thing currently is that there is transformer-based models. There is quite significant work on investigating the state space models that we have to also use for language, because there we have in inference the significant reduction of memory, as we talked, that we don't have to store like the whole KV cache. But at least for the really big models, they are not yet on par in computation. So what you see is here like the architecture of GPT. I think this is still GPT-1, but the other ones we'll see is mainly like scaling things up. So it's similar to what we have in the original transformer, and with positional encoding, then we have mask self-attention, layer null, feed-forward layer null, and then we do that all the time. And this was done. So you see, it's mainly the same as a decoder on the original transformer model, except that we of course don't have the cross attention, because we don't have any encoder, so we only have encoded attention at the decoder side. Any questions first? What is a bit the size to get like, so because I mean large is like one important thing about the models. To get a bit of an idea here, the size tables from GPT-3 and GPT-2. So you already see, so we have GPT-1, which had like 100 million parameters. Then you have like around 300 million parameters. That is is the size of like the BERT model. We had that in self-supervised learning, which at least for NLP was a very common model and often used. You saw that then already by a factor of 5, this was increased to 1.5 billion parameters. And that was then the GPT-2 model, which has around 50 layers. And I often talk still about like 1,000 dimensions, so it already has 1,600 hidden side. Then there's another big step into making models bigger. That's like the GPT-3 here, or the 175 billion model, sorry, which is then the default model which we have for GPT-3. You see the number of then we have nearly 100 layers, and the hidden dimension is something like 12,000 elements here. So we really like increased it. Maybe the good thing is, since then there is already quite some time gone since GPT-3. Problem is less and less people publish. Like in GPT-4, there were no details about that anymore. But we don't see that like there's a continuous explosion of this type of parameters. So I think, for example, Llama models, which are open source, the biggest one, the default one is maybe 70 billion, so even smaller than that. Here at the university, we do a lot of experiments with like 8 billion models. And I mean, they got significantly better. So it's not that we are like increasing over and over again, but we see that, yeah, there is really huge models. And that's one major benefit of these models, to have that many parameters to do that. Okay, before we are now going into looking, okay, how many parameters should I use? Any questions about that? Good. So now just imagine you want to train like a really large model from scratch. Then there's a lot of parameters you have to start. I mean, typically your boss will tell you, yeah, you have X amount of calculation, build a model. And so it's not you can just train forever and so on. It's also about, yeah, you can parallelize, but there's still limits. So there's different like influential factors which you have to take into account. So normally you have more parameters means also somehow more better performance. Of course, there's overfitting and so on, but I mean, these large models we saw here nicely, the model size are always better, and typically also the performance. So one way to improve the model is to make the model size bigger. The other one is, of course, you can also train on more data. So if you train longer on more data it has seen, you typically also get a better model. And so those influence some of the compute. So in general, you can say, yeah, the more compute, the more we are getting. Right? But the question is, for what should you go? Should you increase if you have now a limited budget, should you increase your compute, the data you're looking at, or the parameters? You see, there is something like a power law, like saying if you increase your compute, also your performance gets better. So you see here, on the y-axis, you always see the test loss here, and here you see the compute power, the data set size and tokens, and the parameters, this time without embeddings. And you see in all cases, yes, so there's an exponential dependency a bit. So if you 4 times as many compute, you get double the cost, the performance or something like that. And the question is now, what is like the optimal way? Should I like double my data size, or should I double my parameters, or how should I change these things? Why is that important? There's 2 reasons. On the one hand, it's like expensive to train. So this is a bit like how many petaflops you need, so how much computation you need. You see here is like somehow BERT, so small model, then there's T5 and the GPT family, and we see that it's always increasing. So it's really good to make, it would be good to make a good decision, and it might be that we not can try everything. So for like a GPT model, you cannot now try, I try five different versions with 5 different parameter sizes and select the better one. For a small project, you can try and do a grid search, but it was calculated at that time, if you really would buy the GPU power to calculate GPT-3, it's like around 4.5 million euros to just only the training without any test runs, anything. So only if you once charge the job and run it, that would be roughly the cost. So you can imagine it might be expensive to try like 5 different versions and then select the best one. So the question is, can we somehow estimate that before? It's not only about cost, of course, it's also about energy. So this is the CO2 emission of training these models. And you see, yeah, it has quite, I mean, of course, it may be a bit of selective, but you see the emissions you're generating with once training these types of models is really expensive. So it makes sense to think about what is the best way and how can I efficiently train a model and somehow get the best performance given a limited budget. So that is the question that we want to address a bit. So we want to efficiently build large language models, and you want to get the best performance for a given budget. And the budget we are using as floating point operations. The big approximation, but a bit of to get a first idea. And then the main parameters we can change is, on the one hand, we can decide on the number of parameters, and the other question is the amount of training data. Of course, there's a lot more things. I mean, the number of parameters is not just the number of parameters. Now you can decide, is it better to have a deeper model? Is it better to have wider hidden layers and so on? But we want to simplify a bit things, and it's only about the number of parameters and the amount of training data that we're looking at. Yes?
What about the number of iterations?
I think in this that's a good point, but I think that is somehow included here in the training data. So in a that's like, yeah, more, maybe it's not training data, but it's like how many times you look at one data point, I think. So especially for very large models, it's often happening that you really just do one iteration over the training data. And of course, you can try to get more, use less data by looking at the data point several times. But if you think about self-supervised training data, at least easily we have enough. So we can train really just continue on all data and then normally it's better to add more data than to reuse your existing data. And so yeah, in this calculation, the amount of training data is more like the amount of data points you look at. And of course, you can also look at the same data point several times, or you can just look always at different data points. But yeah, very good point. And for this type of analysis, what people are using is that somehow the number of calculation is like proportional to 6 times n times d calculation. So the question now is, of course, how do you come up with 6 times n times d? And there is like, yeah, very brief heuristic on that. So let's see how people come up with this type of approximation. So if you look at, typically, if you have a parameter, how does it influence it? Typically, the parameters are part of your metrics. And so your weights and the weight is a metric. So you multiply your hidden thing with these metrics. So that's really the most simple thing. You only have feed-forward. So it's a strong approximation, but yeah. So what that means is, yeah, for each of the parameter in the forward side, you once do a matrix multiplication where it's happened. So you have one multiplication and one addition. The size of the matrix is proportional to roughly this n. So each, I mean, of course, you have not one matrix where all the parameters are in, but you have many matrices, and altogether there's like each parameter occurs in one matrix. And then a forward pass is roughly 2n times calculation, because you have to do the multiplication, then you have to do an addition, and that you have to do for each parameter in there. So for each forward pass, you have like roughly like 2n times d calculation. So you do a forward pass for each data point, and then it's 2 times n times d calculation there. On the backward pass, you have to do the derivation. You again have to look at each parameter. But now you can argue that you have to look at each parameter twice. Once in the backward pass to calculate the derivation for this parameter. But if you remember, then we not only have to calculate the derivation with respect to this parameter, we also have to do the backward to calculate the derivation with respect to the hidden representation. You have to do that so twice. So double as much calculation, so 4 times n times d, and in total that's like 6 times n times. It's a very rough estimation. If you think about self-attention, you don't have only, I mean, what you mainly only do is like the first linear layer, and all the self-attention calculation you're ignoring here. So it's a very, very rough thing, but it gives us a first idea like how they are connected. Any questions to this? Yes.
Are these scaling laws independent of architecture? So is it true for both transformers and SSMs?
I think they are, I mean, the two examples we are looking at, they mainly investigated that for transformers. So they are more focusing on how well they transfer to others. I would be skeptical. Maybe there has to be in other scaling laws. We are today looking at these two examples, mainly because most language models are currently using like transformer-based architecture to do that. So if you have that, then the question is, if this is now, if the computation is fixed, how do you select N and D? And you have a bit of the trade-off. You can train a bigger model, then you have to train less. If you have a smaller model, then you can process more data. And this is your budget, and you can somehow fairly compare these ones, and you say later for training, I used 5 million. Of course, there is a lot of more other things that might influence later your decision. Does anybody have an idea what other influence that could have had on other? Just think about when we looked at what you want to optimize in your calculation.
A bigger model always means that you have more inference costs.
Yes, exactly. So that is ignored here, the inference cost. So of course, if you now have the model at inference, you have once a smaller model, so a lot less calculation, or a larger model. So even if the performance would be the same, maybe for that reason you would prefer that one. But here it's really just purely looking at, you have a fixed amount of money, what is the best model you can get with that, only looking at the training cost. And by looking at different examples, there was the initial scaling law by Kaplan and all. They tried a lot of different models. They varied the data size and the model size. Of course, not the size of GPT, because that's might be too good. But again, on smaller models, you try to get a picture of how big it is. And the main finding is, so if you first just take a fixed size batch size, if you increase your data by a factor of 1.5, then you should increase the number of parameters by a factor of 2. If you optimize somehow the batch size, you can even get better performance. When you increase your data size by 1.3, then you should increase your parameters by a factor of 2. So you really like have a significantly larger increase in the parameter size than the data size. So it seems to be better to have more parameters and not increase the data size as fast. That was like the first finding of these first type of initial scaling law that they have done. And it should give you then some hints on like, okay, how should you use both of them? And based on that, there were more, and that of course led then to a set of models. I think this one is even by OpenAI, so it's like a bit the idea behind the GPT models. Then there is a second work on that for a modified scaling law by people from DeepMind, and they looked at a set of models. So the question is, how do you generate a set of models? And the first is they fixed n, so the number of parameters, and then they trained it on 3 different data set sizes. And these are the things here. So here you have the n, and then with the n, with each n they made 3 points. with different data sizes, and then of course that leads to different points here on there. On the x-axis, then you need different flops. So if you train the same model on more data, you need more flops and so on. And then you see here in the gray a bit the minimum. So that's what you want to have. So you want the lowest training loss for GPU. So in this one, for example, for having this type of calculation, you could use this model, this model, this model, or this model. And then, of course, it seems to be somehow best to use this model because that has a lower GPU time. And they did more. So another way of creating a lot of models is you fix C, you train a model with different parameter sizes, and then you choose D in a way that you exactly need this type of computation. So it's more like the question is, how do you generate your different types of models so that you can check then what is like the optimal choose in order to get your. They did 3 different methods. The 2 important ones like minimum and easy. And then you can check, okay, what is now the optimal coefficient? So the idea is, what is the optimal n? So how should it depend on the computation up to 1 parameter and also for D? And they came to a bit of a different type of results. So you see with all their experiments here, it seems like, yeah, the size and the parameters should like increase in the same effort. So it shouldn't be like in the first scaling law says, yeah, you should increase your parameters significantly more than your data points, while this modified scaling law size, now you should improve them like equally. So if you double your parameters, you should also double your data size and so on. This type of law was then called after the model that they built based on then the chinchilla law, and you see a bit like what does it mean for performance. So this is the model they proposed, which is at that point maybe relatively small, like 70 billion, still very huge, but it's trained on 1.4 trillion tokens. So you see even significantly more than the GPT-3 by a factor of more than 4, although it has less than half the data set. And if you compare the computation of the two green ones, here the gopher and the chinchilla, is roughly the same. So this has 4 times more computation, but this has 4 times more parameters. So that's mainly now the question, which one is better? And they showed this one is really also better. So although you need a similar amount of computation here, you result in a better model. And especially it also has the advantage that you now have, of course, also a smaller model. So in inference, then, as we said, it's even more efficient. This is also a bit the direction of how the llama family models are then used. So they typically also have seen significantly more data with limited parameters. Of course, I mean, it's a bit misleading as a law. This typically is not a law. This is like experimental results. And there's a lot of factors which can influence it. And so there's always also coming new ways of how you can optimal choose these type of parameters. Yes.
The scaling laws were only for, well, scaling the parameters, right? So how do you get the initial distribution of how much should go to what aspects? So how much for the data and how much for the parameters? Can you do hyperparameter tuning in cheaper settings and which generalize well to a lot of computation?
I mean, that's what they tried. I mean, they didn't try their experiment with this large model. So they did their law on smaller models. I don't know how big. I mean, how I would have to check it. But in this table here, they didn't use like you see they go up to 10 million parameters. So they tried models between 75 million and 10 billion parameters, and then they tried to come up with a law on like how much data and how much computation to use, and then they apply the law here on a 70 billion parameter model, and at least their compared to this one, it's still holding. So that is the idea that it hopefully can transfer also to bigger models.
And does that hold true for hyperparameter research as well?
What do you mean with like how big you mean, for example, the width and the depths and so on?
For example,
I'm not sure. I think they do some, also scaling of that. But yeah, that's then an additional what you also, I mean, you can again there not try everything. Any more questions? So this is a bit like the idea of how these architectures are, and you saw a bit how you do define your architecture, especially also like the combination of architecture and data. So if there's any more questions to the architecture, we can discuss them now. And otherwise, we can look into a bit into now inference. So how can we use this type of models? And especially when using these models, there is like the interesting thing of like prompting and in-context learning, which gives new ideas and new applications. So what our language models are really interested, or what is very interesting about, is that they can do what is called zero-shot abilities. So they can do new examples or new tasks without having been trained. So traditionally, if you do machine learning, what you do is you train it to do a task, and then you evaluate it, how good is this task. Of course, you look at the generalization to other examples of the same task, but generalization is typically the most challenging thing in order to do that. Here, by relying on just predicting a very simple task, we have that. So the next word prediction is a very, very simple task. You just say, what is the next word? And with that, you're trying to like form now any task that we have into a next word prediction task. So how does that work? So for example, if you have like the question of doing named entity recognition, so you want to know what are the names, then you can transform that into a completion task. So you can, on the one hand, do that into a completion task. You say, instead of like saying, putting in the input, I fly to New York, and make that a labeling task, we had sequence labeling, you just say the sentence, I fly to New York, mentions the city, and then now it's the next word prediction task. And if it's a good model, it should now say New York. So you're transferring any type of task you have into the task of completing the sentence. So that's why one way of transferring tasks, traditional tasks that you have, into next word prediction tasks. And you can use that both. You can use that for generative tasks, that is here. You can also transfer it, for example, to discriminative task if you want to analyze whether New York now is the arrival city or the departure city. You think about a dialogue system where you need to like find, okay, you want to map a request into like doing a request to a database, then maybe you need to find out arrival, or then you can do like somehow measure the probability of I fly to New York means I depart from New York, or I fly to New York means that I arrive in New York. And if you have a good model which is good at predicting next word, then the second sentence should have a higher probability, because that is somehow more probable. While here this shouldn't have a high probability. And so again, what you have done is you transferred the task that we somehow traditionally had, a classification task or anything, into a task which just does next word prediction to do that. All this is what nowadays you know as prompting, where the idea is to encourage a pre-trained model to make a prediction based on the prompt. And the nice thing is that typically most of the tasks we're having, we can transform in this type of next word prediction task. So if you have question answering and you want to know who developed JDK, you change now this question into a full sentence. JDK is developed by, so that can even be done more rule-based. And then it's now just a sentence completion task again, and hopefully you do Oracle. And yeah, some of the one, if you've seen that many times, it's some of the most interesting to me. If you want to write a summary, how can you make a model to write a summary of a text? Again, try to make it a next word prediction task. And the other important thing is try to make it as similar as your training data so that the next word prediction task is really exactly that is, I mean, a language model is reproducing typical effects of your training data. So what you have to do is make it into looking similar to training data. Where do you see a lot of, if you train on the whole web, where do you see a lot of examples of summaries? I mean, there's a lot of websites which at the end, for example, at the beginning have something like TLDR, too long, didn't read, and then there is a short summary of what was all written there. So how can I make now summarization as a next word prediction test? I put the full language there, the full text there, and put afterwards TLDR. Now, what is the most probable way of continuing? If you think about how things are in the web, typically afterwards, if there's TLDR, is a summary of what was there before. So you now make this idea of prompt of summarization, the task, make a summary, you make it into a completion task by doing that. And that is most of the idea of prompting. And when you're like, I guess you've heard about prompt engineering, like how to make prompts. There's always one important question is, can you make your input in a way that it's then very easy for the language model to continue in the way it was trained for? And you can do others like birds can fly. So if you want to know whether, so there's a lot of these ways where you can just make typically a lot of tasks in the way of just completing what people have done. Any questions to this idea? Yes.
Is this used on normal user queries? Like if a user was to have a query that wouldn't generate a good answer, is there some kind of automatic mechanism which translates this into a better prompt for the model?
And what there is more done is where we'll see later, there is a bit of a mismatch between prompting and user queries. And that's why all the large language model you nowadays use, they're not only trained to do next word prediction, but we'll talk later, they are like later than tuned to be better like assistants, so to better follow the type of instruction, which also makes a lot of the prompt engineering not as important anymore. Because if the model is good in understanding that, it can also learn to be more what a prompt engineer is and rephrase it himself. And there works on like, doing prompt engineering by LLM. So you give it a prompt and rephrasing it, and you can train. So there's a lot of, but we'll see there's easy ways of more following the user request. Good. Yeah. So what you can do is see here is a bit how things are exploding. So this prompting get really like a lot of attention, and like starting from 2021 already, people were like writing a lot of papers about how you can prompt this one. So it's a very, very interesting technique of how you can like encourage a language model to do things and to solve tasks. So there is a very important thing. So how you make a model, how you can make a model to solve a task. So in prompting, you describe the task in natural language, and then it can do the task. So for example, you can translate English to German, then school. How does it traditionally work in transfer learning? What we're doing is we are first training our model on just next word prediction. And then you would fine tune your model that if you put in house, it should house come in. You do gradient after. If it does car, it should also be out, and gradient and so on. And then hopefully later it will do automatically. So that's a typical way you make a model to only perform one or specific task. But the interesting thing in prompting is that we are trying to enable the model to complete the task and understand more natural language description of what it should do. So now there is, of course, a lot of ways of how you can put a prompt. There's different ways. Just to give you a bit of an example of how you can transfer that. So in general, the task is we want to do a natural language description. We have our input and we have to somehow extract our output. You see that there's now different ways of prompts. This is what is called a closed prompt. So where the output is even not at the end. So you can have, if you do sentiment classification, you want to know is this positive or negative, you can have this type of template, you put your input, and then you put overall it was that movie, and then you try for different possibilities of that. So if you have I love this movie, then you have I love this movie. Overall, it was a movie, and then hopefully fantastic and amazing is good. And if it says bad would have a low probability. So you can then, for example, if it's a dispute thing, you can try 5 different types of tokens there and then select the one which is best. If you want to do an entity recognition, you have a template. X1, X2 is an entity. Z is a Z entity. So for example, where you have Mike went to Paris and you want to know what Paris is, you can make a prompt like Mike went to Paris. Paris is a Z entity, and then you can try different things for that. So you can label the word with your different types of classes. You can do the summary. So one thing is there. I mean, nowadays there's a lot better ways of doing. It's just like the first straightforward. If you want to do a summary, you can do the TLDR, natural language processing in the field, and so on. And then you do TLDR, and it will give you the summary. And then there is translation. There's often this template with English, double point German, or please translate, and so on. So there's a lot of different ways of how you can put it. And that is especially in the beginning, the models were like sensitive to that. So for translation, for example, people show that you get a better quality than you say when you don't say, please translate this sentence, but please translate this as a professional translator would do. Which is maybe a bit awkward that this does matter, but again, then you maybe if you put in as a professional translator would do, you would find more examples where there is like, or you would more behave similar to the follow-up when there were websites created by a professional translator. So it uses this context to think about it more as retrieving similar examples. Then of course it makes sense to put like professional in there and so on. Yeah, so that is the main idea of prompting. So it's really the big difference is that it's a different way of making a model perform tasks. So instead of giving examples and like learning by these examples, we can solve tasks by describing the task. And that is something which, yeah, wasn't easy without large language model, and I would say is a major step because this is an ability we didn't have before. So there we can only like generalize from examples, and here you can generalize from a description of the task and also solve the task. Yes.
When in training, do you do the prompt addition after the main data set is closed, or do you just?
I mean, this is normally not done in training. So this would, I mean, we see it a bit for training, but typically this is how you do it in inference. So, I mean, you can train just on the next word prediction. That is our baseline. We see it's better to also do to this type of training. But in the first basic model, this is even possible if you only train next word prediction, and then this is done in inference for the inference.
Okay.
We'll see that soon that it's also helpful to later train to follow these types of prompts. It's like instruction following, but a baseline can also do that. And it should do it possible to do it a bit also for just pre-trained models. Good. Any questions? Well, with these prompts, you can also do more additional things. And one thing is what is called the so-called in-context learning. So there the idea is that, yeah, can we also, instead of what we normally do updates and change our model, you just put your learning examples in the context, in the prompt, and then you do a complete completion. And the nice thing is that also works. So if your task is add the two numbers 6 and 8, the idea is you can of course now do it like try to get the answer, but again it's normally easier if you have seen similar examples. So what you can do is you can so add up the number 6 and 2, and then you have 1 plus 2 is 1 plus 1 is 2, 2 plus 5 is 9, 6 plus 8 is, and then you let the model compute it. So you have given examples how you expect it, and then the continuation hopefully should be the same. It should do the same type of examples. So you give also in the context few short examples. The nice thing is that really leads to few shot learning. So there's a lot of few shot learning, but the question is how many shots do you need? And if you really do weight updates, typically it's more like 10 to 100 examples, while this type of in-context learning, you're successful with 2 or 3 up there like examples and already get better. Another example is, for example, if you want to translate, you not say translate to German, but you give it a list to continue. So you say house is house, car is auto, school, and then what is school. It's a bit like the completion task you maybe know from school. There's like 3 examples and you need to do the completion of the 2, the next thing. Of course, this leads then to other types of challenges. So for example, if the question is often you have more than 3 examples, but you have a limited context size, you can't give unlimited number of examples. And then the question is, which examples should you add? And for example, a typical thing is it then makes sense to use similar examples to your output. If these examples are more similar to your training examples, then you get a better performance because then the transfer the model has to do, like from the context to the next example, is less. So you have done them. Also, then going in the idea of what people nowadays call retrieval augmented generation. So they really like give additional context in the prompt. So you search for similar important information, put there before then you then do the completion task. And the other question is also even, and that's maybe a bit more problematic, the ordering is important. So that's because you process from left to right. There is like things are maybe which are at the right, at the end are more important because they are more near to it. And so the ordering of the examples has an influence later on your pointy that you're doing. Any questions? So how good does this work? And here's some numbers. So this is numbers from GPT-3. So you see here what is called superglue. That's like a general language understanding evaluation. So there's a lot of like 100 or so different tasks which are evaluated by on the model. If you do random guessing, you're a bit below 50%. And then you have here different fine-tuned BERT models, which was a default easy way before. So what you see then, if you just use GPT and doing no training, just doing it as by prompting, you get less than 60%. Then if you do very few examples, you see large gains, like you're going into how good a fine-tuned BERT model is. If you do more examples, you're even getting better than the BERT classic model. You're not getting nearly, I mean, of course, if you specify and specialize on one task, you often still get better. So this is like Soter and Human. But the interesting thing here is you really need very few examples only. The most is here that you have 32 examples. I mean, for most tasks, if you want to do a task, it's not super difficult to get 32 examples. And then you don't have to do any type of training. You have the one hammer which can solve all the different problems. You just need to give some examples, and then you get a decent, good performance. One additional nice thing is that, it's even getting better with better models. Also, the gains you get through few shot learning is even more. So here you have the big GPT-3 model, 175 parameters, and there are 2 smaller versions with 13 and 1.3 billion parameters. And you see, this is 0 shot on this type of task. There's like some difference, but the bigger model is not completely different. But then you get really huge gains if you do one shot or few shot learning, and here the gains are a lot lower. Which of course is always nice, meaning the big model not only gives you improvement there, but then you even get more and more and more improvement by the big model. Good. Any more questions? Then one more very short thing, which is often used and is a bit related to that, and that is what's called chain of thought. And which mainly means oh, your answer will get better if you're not only asked for the answer, but also for the explanation. So you have here the task. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can have 3 tennis balls. How many tennis balls does he have now? So you see typical exam questions in math. I don't know which grade. And then the answer is 11. And if you so here's like a one-shot example. So you in context learning was one example. Now you give you another one. The cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? And the answer is 27 seems not to be right. So that is, of course, always a challenge, especially in calculation. Things are not super good. The interesting thing, if you prompt the model to not only give the answer, but also gives an explanation of the answer, you typically get better results. So the only thing that is different here is that you do what they call chain of thought prompting. So you tell him the model shouldn't be just the answer is 11. It should be Roger starting with 5 balls, 2 cans of 3 tennis balls, each are 6 tennis balls. 5 + 6 is 11. The answer is 11. So as you know, also from school, you should not maybe, depending on your exam, you should not only give the answer, but also like the Rechenweg. I don't know the English term. And so you're doing the same thing, so the chain of thought, and then now the model will, of course, hopefully follow this and also do the same thing before. And then you get here an explanation, and you see the same model, this is the same model now outputs correctly 9 instead of 27. So, of course, I mean, and this is not only a cherry-picked example, there is a lot of evaluation on that. And especially with large models, you get improvements by encouraging the model to not only output the answer, but also an explanation. There's a lot of challenges and work around that. There is, for example, the question, do you really have to, is it just that you have more computation? So there's also work that instead of outputting really words, you can just output dot, 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 dot. And it's also doing more and more calculation and give you better answers. So there is still open research, but the idea that you're doing more and more calculation, that you're not only answering, but like dividing the problem into sub-problems and so on, is also working here in making things better. Yes.
How do you train the models that use this dot 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 representation? Because it's essentially conditional computation, right?
Yes, I mean you can even try it to do in context learning. So if you give the model here as answer dot, 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 the answer is 11, then maybe also do it here. But there's of course more advanced method also which try to train the model to really do this type of calculation. Yeah, I mean, there's a lot of this compute times or decoding time, test time scaling and test time compute. So where there's work on like how can you make models like do additional calculation at inference time so that you get a better type of model. Good. Any questions on the inference before we go into the training? Yes.
If you increase the model size, you have a better few-shot performance. Should that also influence the decision with the scaling laws? If you had a model that was bigger but used less data, would that still be better few-shot performance?
I have no idea, I have to say. I don't know. I haven't seen, I think they normally evaluate it. I mean, now that's the question how they evaluate. I would assume they evaluate on few shot or even they even evaluate only on a next word prediction test, so on the training loss. How that then transfers to few shot learning, like to really task performance, is another question. Because, and that's what we're coming on, typically when you train a model, the self-supervised learning by now is only the first step. You do then other steps, and that we want to look now. So of course the default thing, the first thing is the self-supervised learning, which allows us, next word prediction. And a good thing we have said that is that you not only get one feedback signal per sentence, but you get for each word a feedback signal. And that's why we also come up with this disadvantage that we have no separation of input and output, that we have unidirectional processing, but however, with large models, that's currently decent. However, if we just train for next word prediction, we have a bit of a misalignment. So in training, we're doing next word prediction. So we're doing just what is the best way to do next word prediction. But in testing, and that's what we had mentioned just before, what we're really interested in is how helpful is this to assist the user. And there might not be always exactly the same thing. So to give some examples, if you just train it on all codes, on own code in the internet, your aim is to later have a model which is good at coding, so it should generate code. But if you also train it on all the incorrect code which is there, it might be inefficient in the end. Of course, the hope is that most code that you find is somewhat correct because it has been checked by people, but you all know that's not the case. So you might also learn to do wrong code and so on. Another example, which makes it even more clear, is maybe if you prompt the model, explain the moon landing to a 6-year-old in a few sentences, then you would hope that the most probable answer to that is the explanation of that. But if it's just trained on the internet, a very probable continuation of that is also explain the theory of gravity to a 6-year-old and explain the theory of relativity to a 6-year-old in a few sentences, because this is how a table of content or FAQ list would look like. And so this is also a common way to extend this prompt, explain the moon landing to a 6-year-old in a few sentences. So while this is not good as on the user perspective, it is a very good explanation, or like a very good next sentence prediction, because you'll have a lot of table of content, and there this might happen very common. So if we're just doing this one, we have this problem. There is a misalignment, and furthermore, you have a lot of unintended behaviors. It might be not following your instruction. You have the typical thing that it's making up a lot of facts. It might be generating very biased and toxic text. I mean, it's just trained on what is in the internet. And I guess we all know that what is in the internet is a lot of interesting things, but there's also a lot of crap in there. And somehow you want to do that. So the question is, how can we adapt to this scenario? So how can we make a model that's not only doing next word prediction, which is a good task, but what we really want to do is it should answer the question that we give, or if we give an instruction, so if we give an input, it should give us a valuable type of output. So what will you do? You're training neural networks and all that thing a lot. So with all your knowledge, you have answered. Now, how can you make a model now that's not just like putting out the next word prediction, but being really useful? Any idea? Yes?
We can train it on different tasks.
Yes, exactly. So yeah, training on different tasks is good. And I mean, now you can make out of different tasks one task, and that's what people then call instruction following. So the idea is, from all the things we're interested in, we're collecting our data, and we're making all these tasks into one task, which is follow the instructions. So you no longer give only, like if you have translation before, you give not source sentence, target sentence, you make it into a prompt. So translate this sentence into English, and then you give a German sentence. So all your data sets you have, you transform them into instruction following tasks. And then we can just do supervised fine-tuning. And then the idea is that the model later will follow, hopefully, all the instruction has been trained. So the idea is you have a collection of data set, and you have the task given as instruction. So you fine-tune them all, and then hopefully you can generalize also to use them. So you have something like, please answer the following question. What is the boiling point of nitrogen? And then it will hopefully answer that correctly. You also can have then chain of thought things. So you have there a lot of different tasks. So in this paper, Supernatural, I think they had 1.8 thousand tasks. So not data points, but different tasks. For each of them, they have different things. And one important thing, which is maybe then different, is we are no longer evaluating the models then only on the task that we've trained on, but we want to also generalize it to unseen tasks. So some of the next step. So you not only want to generalize to unseen examples of the task, but you also want to generalize to unseen tasks. And that, of course, is only possible because the task is no longer either implicitly in there, because that's what you expect, or you have maybe a special token, so discriminatively, but you have now a natural language description of the task. So the model should also be able to understand this description and solve the task. So here you have the definition, for example. So there's the supernatural, which has 76 task types, 1,600 tasks, and then instructions. So here it's given an utterance and recent dialogue context containing past three utterance. Output yes if the utterance contains a small talk strategy, otherwise input no. And then you describe what it is. You give the context, the output, the explanation, and the context, output, explanation, and so on. And so what this data set mainly is it took existing data sets or created them artificially, and now you can train the model on these tasks. So you're having input, output, and explanation maybe, and you're training the model to generate them. So that is really like making the model then to follow this type of explanation. You see what is there. So there's translation tasks, question answering, sentiment analysis. So there's like a lot of way of different types of tasks. And then you can look, does it work? And the nice thing is that really like you see quite nice improvements. So this was done on T5, which is still an encoder-decoder model, but we'll see several things for also decoder-based models. You have here the number of parameters. You have the baseline score normalized, and then the score out the fine-tuning. And of course, what is better or than hoped for is, yeah, you're not only getting always better, as seen here by the delta. How much you get better is again also even larger if you have stronger models. While at the beginning the difference weren't too big, here you're getting really like large improvements over it. So you can get better and better with larger models by aligning them with what you really want to do. Of course, there's again, then I mean, you have to have a good, large enough data set, because there is a problem of catastrophic forgetting, that it might be only good at the task that you're training it. So the generalization to new task is important. Also, it might be that you want to vary your task descriptions so that you're not only giving like one prompt of how to solve the task, but different ones. But in general, this is an ability to make the model really follow these types of tasks. Yes.
I think in the second or 250M model, the FT value
is
has the wrong sign.
Yes, that is right. Yes, thanks. That should be the case. Yes, I would hope so. Yeah, thanks. Good. Some examples are, so here is this false or not false, or false is, and then let's think think step by step. Then you have here the output of the baseline model, which is at the end false, and this is then the fine-tuned one, so the instruction fine-tuned, and you see that the model is able to like do like it stepwise instead of here it's doing false or not false. The first one is true or false. Here is true, the answer is true, and then it's giving the right answer. Another example is here, where you also should think by step, and again, the model, the baseline model is not able to do that, but the final model is doing. So this is like one way of training your model, is to do really this type of supervised fine-tuning. So it's the same type of supervised fine-tuning that we had before, but we're having transformed a lot of different tasks into one task, which is follow the instructions. Good. Any questions? Yes.
Do you do this fine-tuning with adapters, or do you have to have some countermeasure against forgetting?
That now depends. So I think in for this flan and so on, they even train everything because they have so much data that you can even train everything. If you do it yourself and doing it like for a limited number of tasks, you might use adapters because then one thing, your data size is smaller, and secondly, it's of course also the GPU calculation to do. But you can do it in base. It more depends on how much data you have here. However, there is still one type of problem, and there is, of course, not always a single correct answer. So there might be several correct answers, and if you look at correct or wrong answers, they might be different, bad or good. And there is a bit of a mismatch. So in training, you do a token level matching. So if you think about supervised training, you say this is the correct answer, you increase the probability of this answer. So just like saying each token, it should be exactly like that. In final evaluation, some mistakes are bigger and smaller, so you more look at the whole sentence and try to do that. So there is a mismatch again, still onto what we're doing in training and how we're evaluating. It's not as big anymore as before because we're not doing next word prediction and then doing another task, but still it's like how we evaluate whether the answer is right or wrong is still different. A user might say, oh, this answer is still valid, but just like different formulated, that's not done in training. And on the other hand, it might be that it's very similar. So you only get a very minor mistake, but if the word not is missing, it's only like one mistake, but a big one from the evaluation. So the question is, can we do it even better? And that's what we'll talk about in the last 25 minutes. And the idea is, can we directly try to optimize the human preference? So can we directly try to optimize, does the human like the output, how the system has output? And in order to do that, what people are using is reinforcement learning. So we'll do it very briefly, as I said, a very high overview on that. But the idea is how we can do then this type of reinforcement learning to even better align the output of the system with what the model output. What is human preferences? So imagine you have language model, for example, for output, and this language model can generate you now different samples. And then you can ask the user to rate it, and you might have different ratings. An earthquake hit San Francisco, there were minor property damages, but no injuries. And you have the Bay Area has good weather, but it's prone to earthquakes and wildfires. I mean, the last one is somehow a right sentence, but if the summary was about one concrete earthquake, the first summary should be much better than the second one. So you can give ratings to the review, to the summaries, and then the idea is, can we now optimize the model in a way that it's like generating summaries or generating outputs which have a high agreement with what humans do. So what is our goal? We somehow not want to reproduce the correct answer, but what we want to do is like that the expected reward we get from the system should be maximized. So the expected reward you get for your answer, that should be as high as possible. So you're only like, you're trying to generate output so that the reward that a human would give to it, the grading, that should be as high as possible. How can we do that? So we can't do that directly in the supervised learning because then we have to give for each word a feedback and measure somehow cross entropy. However, there is what is called reinforcement learning, which has been used especially for a lot of other areas. For example, for games where they have the big advantage that this feedback is easier. So if you have a model which plays a game, you can later say you have won or you have not won. So that's easy. But in language, of course, this reward is quite challenging because how do you measure how good this type of summary is? Normally, you have a lot more data on what is a correct summary or what is an automatic summary than like evaluating different summaries. But we'll see how we can address it. But in general, this idea of reinforcement learning has been there a lot. And what people typically use here is what is called PPO-based reinforcement learning, where you try to directly optimize the language model to have the best preference in the output. So what do we try to do? We are trying to optimize the parameters to maximize our reward. So you're trying to optimize pattern or parameter so that if you look which sentence you generate based on your model, the reward that you expect from the sentences should be as high as possible. So you're no longer trying to increase the probability of the reference transcript, but now you're trying that the reward you get for the reference is as high as possible. Which means if you're doing the gradient descent again, what you want to do is you update your parameters in a way that you calculate the derivation of this one. So no longer your original, here's a loss function. So the difference between the correct and the output addition. Now you're trying to calculate the derivation of this one, and then you can increase that one. So the challenge is then, how do we estimate that, and how do we especially deal with then non-differential functions? So the reward, we can't like calculate the derivation with the reward. And one thing we can, for example, do is, and we are looking at a simpler example, is what is called reinforce. How does it work? Sorry, we have now, I think, 2 math slides, but it's not too difficult. So what we want is, we saw that in order to do the optimization here, we have to calculate the derivation with respect to the parameters of the expected reward. So in order to do that, let's see what is the expected reward. The expected reward is the sum of all possible outputs that you can have, the reward for this output times the probability of this output. It's just the definition of the expectation value. If you have an expectation value, you always multiply all possible outputs with a probability. If you have this formula, the reward is independent of your parameters. So how much reward you get is not depending on the parameters. Only what is depending on your parameters is the probability. So you can move in your gradient here and like move the reward outside. Yeah, now you can use what the log derivation trick is, and that is that the derivation of the log of the probability is now the 1 divided by the probability times the probability of the derivation of the probability. That's the normal way of how you calculate the derivation of logarithm, is 1 divided through this value times the inner one. That's normal, like derivation law. If you reformulate this one, you multiply with that, you get the derivation of P of S is P of S times the derivation of log P of S. It's just like the normal definition here, multiplied. And this one, we can now here, we can apply it. So what we can do is like, we can replace now the left side here with that one. And we're getting here. So you have P of S, that's from here, and log, that's here. So this one is the left side up there, and the right side is split it up here and here. And now we're nearly done. So this is now, again, the expectation value of RS times the derivation of log P of S. So what you have now shown is that the derivation of the expectation value is the expectation value of the reward times the derivation of log. And that we can now use. So we said that in order to calculate this one, we can also calculate it as the expectation value of RS times the derivation of the log. There we can estimate a bit like 1 divided by m over some samples. So if we're just, what we can do instead of summing over all possible s, we'll randomly sample m and say they're all equally important. Then the reward for that times the log probability. And if we put this one into our gradient update, what does it mean? So now we can here calculate the gradient. update. We don't have any expectations more. So what we're just doing is we're doing the average over some samples for the input, the reward for this sample times the derivation of the log. That means if the reward is positive, we take a step to maximize the gradient. If the reward is negative, we step a step to minimize that. So very simple. And we see a bit of cost because what we now do is if we're training is we have to generate several examples. Then we get a reward for each example, and then we're updating them. So if we're really doing human feedback, that might be very costly because you generate a lot of summaries. Then you have a person like evaluating them, and then you have to do that again. Maybe one question, how do we generate many examples?
Use user queries?
No, but you have the same input, you want for the same input, now different. So for example, you have the same text and you want now several summaries for that because you want to do that. And they should be all nearly equally important, equal probable.
That was a mechanical verb.
You can't, this should be done by the model. You have to do it by the model. How can you use one language model to generate not one sample, not one summary, but several summaries?
You could just ask it to generate different summaries.
Yes, it might even be work, but you can even do it mathematically or like with a model without. Yes?
Add noise, like with the input.
Yeah, no, you don't have to add noise. I mean, when you generate with a language model, normally you always take the most probable token and then do the next one and so on. What you instead can do is sampling. You're not taking the most probable, but you have a probability distribution. You randomly choose one. And then you're not getting random outputs because, of course, you randomly choose according to its probability. And some words are more probable, so you mostly take the more probable one. But this is what is used also in a lot of language models. In a lot of scenarios, you don't want to have always the same answer. If you think about a dialogue, it's bad if you say hi, it always answers the same way. So in order to do that, what you can do is you sample. So at each time step, when you generate your output, you're not taking just the most probable output, but you're looking at this probability distribution and taking, according to this probability distribution, the next token. In some situations, the model will say, here it's only fitting one word. So you'll mainly always take this word. But at others, especially at the beginning, if you say hi, so then the answers, there's a lot of possible answers. It can also say hi, good morning, good afternoon, a lot of things. And then it will randomly sample from them. So there you have a chance to easily get there a lot of random samples. So with this, we are now somehow nicely can train our model. So we're doing pre-training. Then now we can do reinforcement learning where we take our model, it generates some answers. There's a human given feedback. Then we can adapt our model and it will learn to generate outputs which have more and more rewards to do that. So that's very nice. So now we can really directly optimize our model to not only give most probable answers, but to give answers where a human would give a high reward. There's one challenge with that. Mentioned it already a bit. I mean, it's not really realistic. If you do training, you need to have thousands of examples. So you have a user to like always sit there for thousands of examples, give like ratings and so on. So yeah, maybe you can use mechanical Turk, but it will be expensive. And so the question is, can you do better? How can we do better? You have an idea?
I mean, there is this concept of LLM as a judge. So just using another model to evaluate.
Yes, exactly. So in this case, it's often called a reward model, but it's mainly the same LLM as a judge. So if LLMs are good at replacing humans, maybe they can replace a human here again. So what we're mainly doing is, can we estimate a human would rate that and use this as a reward model? So we have a model which estimates like how a human would rate, and then we can easily train on a lot of examples. So that is like, yeah, the human in the loop is expensive, so let's replace the human by another model. So how we are doing it? The normal thing, we're collecting training data. So first, we have a lot of summaries. We generate summaries, and then we have humans to rate them. Of course, we still have to collect data, and you might have to collect that specifically for the model because you have another model, maybe you get other things. So this is still expensive. But then we're doing the second step. And now, instead of the human, we are training a model to do this type of predictions. So we're training now a language model which takes this as input and should give us a reward of doing that. And then we are doing this, and then we're applying the reward model in reinforcement learning. So then we can do a lot of iterations of reinforcement learning and so on. Of course, it sounds more easy than it is, because if your model gets now very different, the input, the models it's generated is very different. Maybe your reward function doesn't fit as well anymore, but in general, it works quite good. However, there's another challenge, and that is that human rankings are often very noisy and miscalibrated. So if you have, oh, sorry, it's up there a bit small, but if you have something like a 4.2 magnitude earthquake hit San Francisco, resulting in a massive damage, should that be now a 4.1 rating or a 6.6 or a 3.2? Like just giving grades out of no context is typically difficult. And that's why the reward models and the data is collected a bit different. Pairwise comparisons, or in general, comparisons are easier. So what instead of giving ratings, what you're doing is the data you're collecting is only you're sorting things. So what you're doing is that you're saying that this summary is better than this summary, and that's better than this summary. So ranking 3 different outputs is normally easier than giving scores to that. So instead of training, like collecting scoring data, what we collect is rating data. So where it says, okay, we get 5 examples. I mean, you have to be careful, not too many, then ranking is difficult to get, but 3, 4 or so is possible. So you give 3, 4 outputs, and then you're ranking them. How do you do that? I mean, what we want to do is that for each comparison here, that we maximize the probability that the rating of the one which is winning is better than the one that is losing. And then you can do that by calculating the reward function of the first one divided by the reward function of the others, or you have sigma of the reward function of the first one given the reward function of the second one. So what you're really doing is you're collecting this data, X, and then a winning and a losing sample, and then you're training your model in a way that the probability of the reward function of the winning minus the reward function of the losers get higher, so that the difference between is as big as possible. What type of model we're training? We know language models is good. So what we mainly take is we're taking a language model here, and the only thing we're training is our regression hat. So at the last position, we're training now a new hat, which takes this hidden state and then predicts our reward function. And this is the only thing you're training. So it's not too many parameters, but that's the only thing you're doing, which gets then as input the output, so the input and the output, and should calculate a reward function. And with this one, you can even train it now in a way that you don't need rewards, you only need comparison and still can train a reward function. And you train a reward function so that the order is always the same as the training data. Yes?
This would then count as an adversarial model, right?
Yes, I mean, typically you're really not training them together, and it's not that you're really trying to, I mean, it's not really adversarial because you're not trying to mislead that. I mean, it's similar that two are, but they are more cooperating. The one is saying, is it better or worse? The other model is not trying to convince it that the other way. So they're not playing against this. So it's not really adversarial, but they're still like collaborating more. Does that work? And the nice thing is it's working quite good. So you have here the human performance and the ensemble of many humans. And you see, first of all, the bigger your model is, the better the performance. It's nice, so it's really learning something. The more samples you have, also you're learning better. you're getting at least similar to human, not as good, but just imagine how much more effective this is. And a last big advantage, it's not too much data. So yeah, you need to collect maybe, to be really good, 64,000 examples, but that's not something which is completely impossible. I mean, at least if you're using like online platforms or something like Mechanical Turk, it's possible to collect as many samples. So it's nothing which is not achievable or something like that. Good. Any more questions? Good. Then let's put everything together and see how like this type of reinforcement learning from human feedback works in total. So how it normally works is we're training first our pre-trained model. We have our reward function model, which is also trained on the data. So then we're initializing our target model with the pre-trained model. So of course, that's a good starting point. And then you have your reward function. The reward function is a reward by the reward model. And then there is one additional thing here. Normally, what you want also is the model shouldn't change too much. You don't want to forget everything that you've learned before. So then the reward you see is also like the probability of your new model shouldn't be too different from the probability that you originally. It's again like a bit of a regularization term that you're not changing too much, but keeping it somehow similar. So what is it then? So you have your pre-training, then you do the training of your reward model, and then you do your reinforcement learning, and that's now nearly the full pipeline. How good that works is you're seeing here. So here's for summarization. This is only the pre-trained model. Then if you do supervised fine-tuning, you're getting here. This is human summaries. And you see that if you do reinforcement learning from human feedback, you can get even better than what the default is. So maybe you're not getting better summaries, but at least summaries that are more liked by the student. And that's, of course, a challenge that sometimes these models now try to just please the user and not be useful anymore and so on. So there's a lot of further questions how to align with user preferences. It's like a very huge type of research field, but this is a bit the idea. So to the whole process, so how it typically works is you first do pre-training, that's self-supervised learning. Then you do self-supervised training. We see that there is a misalignment that you give token feedback, but that's not. But it's giving you a first right direction. And especially for these two models, it's often very important to have a good starting point. And since if you do supervised learning here, you have a better starting point and you're already getting at a very good start position. And then you do your reward model to do your fine-tuning, and then it gives you your final model. And yeah, that is then how it's called Instruct GPT. So that's at least the basic idea of how a lot of language models are trained nowadays. Good. So this is it for today. Do you have any more questions? Good. Then thanks a lot. And Tuesday, I think we have another exercise about large language models. And then we'll have the repetition, as I said, on next Thursday.